Hi, in this presentation, we're going to discuss gravity. So, we might have heard the famous story of Sir Isaac Newton sitting under a tree and watching an apple fall and making his great intuitive leap about gravity. But Newton was not the first person to discover gravity. Newton was just the first person who discovered that gravity is universal. So, as he was sitting under his apple tree and watching the apples fall, he realized that the Earth's pull on an apple is the same kind of pull that the Earth exerts on the moon. Before Newton came up with this synthesis, people believed kind of different things about the motion of planets and stars versus the motion of objects on Earth. For instance, Aristotle, a Greek philosopher, believed that the motions in planets and stars was governed by totally different laws, that they had celestial motion as opposed to terrestrial motion down here. But Newton recognized that the same force that draws objects to the earth when they fall towards it also pulls on the planets towards the sun. So he recognized that force is the same. And that was his Newtonian synthesis, that the same set of laws apply to both celestial objects, objects out in space, and terrestrial objects here on Earth. So the law of universal gravitation states that every body or object attracts every other object with a force that's directly proportional to the product of their masses and inversely proportional to the square of the distance separating them. So the more mass that we have in our objects, the more they're going to be attracted. But the further away we put our objects, the less the force of attraction between them. And we can write this as the force is proportional to mass 1 times mass 2 divided by the distance squared. Or we can do it more simply by mass 1 times mass 2 is divided by distance squared. And it's important to realize that just like when we were talking about our starting velocity and ending velocity, when we have the numbers down here, that's just differentiating this is our mass number 1 and this is our mass number 2. But if we have the 2 in superscript, like over distance, that means we have to square that. So this formula tells us the greater the mass of the bodies, the greater the force of attraction between them, and the greater the distance, however, the weaker that force is going to be. So let's say we have two planets and they're of the same, they have a certain mass. Um, and if we could actually double the mass of one of those planets, what would you say would happen to the force of gravity between it and its neighbor? Would it double, quadruple, reduce by half, or reduce by one quarter? Well, let's work this out. So we have our equation there. Force is proportional to the product of the two masses divided by the distance squared between them. So let's say we have one planet that has a mass of 3, another planet has a mass of 4, and the distance between them is 3. And it really doesn't matter which units we use here. We're just looking at the numbers here. So we would multiply our masses, 3 times 4, and that would give us 12. And then we divide that by the distance squared. So we'd have to multiply 3 times 3 and get 9. And when we divide 12 by 9, we get the force between the objects is 1.33. But now let's double the mass of planet 1. So its mass jumps from 3 to 6. And the other planet in the distance stay the same. So now our equation is going to be 6 times 4, 24, divided by 9 because the distance stayed the same. And we get a force of 2.67. So you can see that when we doubled the mass of one of the planets, we doubled the attraction between them. So this force of gravity that attracts bodies to each other is actually the weakest of the four known fundamental forces. And the four fundamental forces are gravity, which we're talking about in this presentation, the electromagnetic force, which we'll talk about later on in this term, and then the strong and weak nuclear forces that act on a subatomic level. But all three of those forces are much stronger than gravity. And you might think, well, then why do we notice gravity? If I trip and fall, I don't notice the electrical uh, magnetic force between me and the floor. I notice gravity pulling me down to the floor with a smack. And that's because even though gravity is very weak, the mass of the earth is huge. So that gravitational pull of the earth is going to be quite great, and we can actually perceive it. There's actually a universal gravitational constant that's expressed as G, a capital G. And if we wanted to calculate it, it's 6.67 times 10 to the negative 11th power uh, Newton squared times kilogram squared. Um, but we're not going to do any calculations with that particular formula. But once scientists had figured out the universal constant G, then it was quite easy to do calculations to figure out what is the mass of the Earth. And we got a mass of 6 times 10 to the 24th kilograms. So that's 6 followed by 24 zeros. That's a huge number. So you can see the Earth is quite massive compared to, say, us. So if we introduce the gravitational constant, now we can actually express that law of gravity as an exact equation instead of a proportionality, which was how we did it before. So now instead of F tilde sign meaning proportional to our two masses divided by our distance squared, we can say our force is equal to the force of gravity times our two masses, our gravitational constant times our two masses divided by the distance squared. So the way they determine G is the gravitational force between two masses that each weigh 1 kilogram that are 1 meter apart. And if you do the math, you end up getting the number 0 times 0.000000000000667 of a Newton. So would you think that's a really large force or a really small force? Well, we've got a lot of zeros behind our decimal there, so that's a really, really small number. And this is what tells us that gravity is a very weak force, much, much weaker than electromagnetic force, for instance. And we only feel the effects of gravity when very large masses like the Earth are involved. And think about this again. You can feel the gravitational pull of Earth on you as you're sitting in your chair. You can feel your weight being pulled down into the chair. But do you feel the gravitational pull from your computer screen or your desk or another person in the room? No, because those masses aren't large enough. So we can't feel their effects. They are there, though. If we had sensitive enough detectors, we could actually see the force of gravity, say, between you and your computer screen, because it is there. It's just so small that we can't feel it. The inverse square law also helps us understand gravity, and that states that the intensity of a force or effect is inversely squared to the distance that causes that effect. So intensity is going to be proportional to 1 divided by the distance squared. And of course, looking at this equation, we can see as we increase the distance, the force is going to decrease. And if we decrease the distance, the force is going to increase. And what's interesting about this is that at great distance, this force can become very, very small and it can approach zero, but it never actually reaches zero. So if we put you on a rocket ship and shot you to the other end of the galaxy, far, far away from Earth, the pull of Earth's gravity would be infinitesimal, but it would still not be zero. But of course, you wouldn't feel it because it'd be drowned out by the gravitational pull of other objects, stars, and planets around you. But no matter how far you go, you would still feel the gravitational pull of the Earth, or still be experiencing. You wouldn't be able to perceive it. And this is true for all objects: the sun, Pluto floating out there, comets passing us by. They have a gravitational pull on us even at great distances. It's just so small, we don't feel it. And we can think of the inverse square law like this. Let's say you have a can of spray paint and you're painting a wall. And if you put your finger on the button and you release a certain amount of paint, If you're at one distance, the paint will cover an area, and we'll call that one area unit, and it'll be a certain thickness. And if you've ever spray painted and you know if you get too close to the object, the paint gets very thick and maybe it'll even run. So that one area unit has, we'll say that's one layer thick. But let's say now you back off from the wall to double that distance and you put your finger on the nozzle and you shoot out the exact same amount of paint. Well, now we can watch, see these lines drawn here. We can see as we get 2 units of distance away, we're going to have 4 area units covered with our paint, but the thickness of the layer is only going to be a quarter of as much. Okay? So as we've gone doubled the distance, we've also had to do the forces the inverse of the distance. So we have to do 1 over the distance squared. So if we go 2 units of distance, we square that 4, so we know it's 1/4 as thick. Okay. And then if we go to 3 units of distance, what do you think we would get here? How many units would it cover, the paint cover, and how thick would our layer be? Well, 3 units of distance, our paint would cover 9 area units, and we would take that distance 3, square it, get 9, and our layer would only be 1/9 as thick. And then if we get out here to 4 units of distance, what do you think the area units and the layer would be? And again, at 4 units, we would have 16 area units covered, but the layer, 4 units times 4 units to get our distance, 4 times 4 is 16, only 1/16 is fit as thick. So you can see the strength of the force, in this case, the layer of the paint, is going to be much, much thinner the further out we get, and it's going to be that inverse square. Same thing happens with gravity. So let's look here on this chart, and at the surface of the earth, we can say an apple weighs exerts 1 Newton of force, okay, at one distance. And that's up here. That's the most gravitational force that that apple and the earth exert on each other. If we get to double the distance, okay, then we have to, of course, square the distance. So 2 times 2 is 4. The apple would only exert 1/4 as much force, and the earth would only exert 1/4 as that much force on the apple. So if we had a scale, we would say the apple weighed 1/4 of a Newton. 3 times the distance, again, 3 times 3, 9, 1/9 of a Newton. 4 times the distance, 4 times 4 is 16, 1/16 of a Newton. And you can see that gravitational force going way down. What do you think it would be at 5 times the distance? And of course, we would just multiply our distance squared. So 5 times 5 is 25. So the force of gravity on that apple would only be 1/25 of the force it would be on the surface of the earth. And we talked about forces and newtons and mentioned weight. And you might remember when we talked about mass and weight. So mass is independent of gravity. It's a measure of inertia. But weight is when we do have gravity acting on a mass. And so what we feel is weight is the force an object exerts against a supporting surface due to gravity, most often due to gravity. So as you're sitting on your chair, you feel the force on your bottom and on your thighs of gravity pulling you down into the chair, and the chair is supporting you. And sometimes weight is also due to other things in gravity. Remember last week we talked about that uh, centrifugal force, which is not really a air quote real force, but if we are in that rotating frame of reference, say the bug in the can that we're swinging around, then that bug feels that force pushing him against the floor of the can, and he has weight. Okay, so that's an example of weight that's not due to gravity, but most often it is due to gravity. So knowing that weight is influenced by gravity and that you have to have a support force, an object exerting a support force against you to have weight. Let's say you're standing on a scale in an elevator. What would you say if you're watching the number on the scale? What would happen when the elevator accelerates up, what would happen when the elevator accelerates down, and what do you think the scale would say when the elevator was in free fall if the cable snapped? Well, let's look at what would happen here. So, if we're in an elevator standing on a scale, and we'll say we're just going to say that this girl looked down at the scale and it said 100 pounds. Okay. So, if the elevator is at rest here, or if the elevator's moving at a set velocity, so there's no acceleration, then when she looks down at the scale is going to read 100 pounds. Yeah. Whether the elevator's at rest or it's not accelerating, she's going to weigh 100 pounds. Now, if the elevator starts moving more quickly up, okay, it's accelerating up. Now the support force is pushing up on her. And if she looks down at the scale, she's going to see now it looks like she weighs 105 pounds or 110 pounds, depending on the amount of acceleration up that she's experiencing in that elevator. Now she pushes the buttons and goes down. As the elevator is accelerating down, if she looks down at the scale, because the support force is going to be less, she might see, oh, I only weigh 95 pounds or I weigh 90 pounds. And then if the cable breaks and the elevator is in free fall, then there is no support force because everything in the elevator is falling at the same rate. And the only thing in free fall acting on the objects is gravity, no support force. So the scale's going to read zero. And in any of these cases, would we say that gravity has stopped acting on the little girl? Well, no. Even when she's in free fall, gravity is acting on her. And matter of fact, in free fall, gravity is the only force acting on her. But she doesn't feel the gravity when she's in free fall because there's no support force. So she doesn't feel that weight anymore. And think about this if you've ever gone to, say, Busch Gardens and you've ridden some of the roller coasters, and it does the little clanky thing as it takes you up to the top of the hill. And then as you come down off the top of the hill and you start that first hill, you get that funny feeling in your stomach, and sometimes you get that feeling of weightlessness. And that's because the roller coaster car has literally dropped out from underneath you. And for a second there, you're in free fall. There's no support force on you. And so you feel weightless on the roller coaster. And then, of course, once you get down to the bottom of the hill, of course, now you've stopped that free fall and you have some deceleration or whatever, and you feel the weight sitting down in the chair of the car. So whenever we don't have a support force, like when we're in free fall, we experience that feeling of weightlessness. So if we look at the gentleman, he took a wrong turn and he drove off the cliff in his car. As he and his car go off the cliff, the support force is now gone. The only thing acting on him in the car is the force of gravity, and he's going to feel weightless. He's going to feel no support force. Same thing happens when we have astronauts out in space. Okay. They have no support force, so they're in a continual state of weightlessness. If we think of astronauts, say, on the International Space Station that's orbiting the Earth, and orbits around planets basically are just controlled free fall. The object is falling around the Earth. Okay. So because it's in the space station itself is in free fall, the astronauts inside the station don't experience any gravity, don't experience any weight. So they experience that weightlessness. I've put a video link on Moodle under resources that shows people riding what's called the Vomit Comet. And this is a plane used to train astronauts to get used to weightlessness. And the way this plane does this is it takes off, it climbs at a steep gradient, and then it makes an arc. It kind of goes in a parabola. And as it reaches the height of the arc and starts coming down, the people inside the plane feel weightless because the support force of the plane has dropped out from underneath them. So for a few seconds, the passengers in the plane experience weightlessness, which you might have done if you've ever been on a really bumpy, turbulent flight. So after the presentation, if you want to see that in action, the link is on Moodle. So thinking about going back to our girl in our elevator, if the elevator was moving downward at a constant velocity, would you look down and see that you weighed less? And no, you wouldn't. Constant velocity means no acceleration, so you would be here in the constant velocity, no acceleration, normal weight. Your weight would not change. Your weight's only going to change in the elevator while there's acceleration either up or down that's present. One effect of gravity that we can see in everyday life is tides. And this is a difference between ocean levels at different times of day. So, for instance, at low tide, you can walk out maybe on this pier and you can see a lot of the bank and maybe even see the bottom, and the boat is way low below the level of the pier. And then if you come out maybe 12 hours later or so, you'll come back out and you'll see, wow, now it's high tide. Now there's a lot of water. You can't see the bottom, and the boat is floating up near the pier. And most places that have ocean tides typically have two high tides and two low tides per day. And these tides are produced by the gravitational attraction between the Earth and the Moon. So the Earth exerts a pull on the Moon that keeps it in orbit, but the Moon also pulls on the Earth, and it pulls on the water on the Earth. And because we know that distance, that inverse square law, that the further away we get from a force, the less tug we have, there's a greater tug on the water and the land facing the moon than there is on the other side. So the moon pulls the water to it. And because the water is not solid, as it stretches, it makes kind of an oblong shape. So it doesn't stay a spherical shape, it makes kind of an oblong shape. So we end up having a bulge on the side facing the moon, but also a bulge on the side opposite the moon. And sometimes the moon and the sun and the earth line up in a line. And that usually happens when we have a full moon with the sun shining all on the entire half of the moon here, or a new moon when the face of the moon is in shadow. And now we have the gravitational pull of the moon pulling on the water of the earth, but also the gravitational pull of the sun. And they add up and they cause what we call spring tides. And these are usually tides that are much higher than normal. They don't really, I don't know why they call them spring tides, because they really don't have anything to do with seasons. They have to do with when the moon and sun and earth are in a straight line. When the moon is a half moon, now we can see the force of gravity. Here's the sun pulling this way, but the moon is pulling at a perpendicular angle. So now they kind of partially cancel each other out. The pull of the moon, because it's so much closer, is still a little stronger on the tides than the sun, but they do cancel each other out quite a bit. And this causes a extra low tide called a neap tide. And so there can be quite a bit of difference, say, in the high tide level of a spring tide and a neap tide. It can be, um, depending on the geography of the area, either a meter or it can be several tens of meters. And I've placed also a link to a video on Moodle that discusses the tides in the moon and earth if you want to learn more about that. But as we looked at the earth and moon exerting forces on each other, they're doing this at a distance and they're not touching each other. So, how is this actually working? How can the earth pull on the moon over all these hundreds of thousands of miles? And one way to think of it is this, that the earth is surrounded by what we call a gravitational field. The moon also has a gravitational field, and they're close enough that their gravitational fields interact. And what a gravitational field is actually an alteration of space around the Earth or any other object that has mass. So it's a type of force field. Another example might be, for example, a magnetic field. So, for instance, if you have a magnet and some nails, if you move the magnet close enough to the nails on your desk, all of a sudden, boom, the nails are attracted to the magnet via its magnetic field. If we want to represent these fields, we can represent them by what we call field lines, and we draw vector lines that show where the force is going, and it's going towards the center of the earth. And so the arrows show us that the force is always going towards the center of the earth. And then the crowding of the arrows, how the arrows are closer together, closer to the earth, indicates that that magnitude of the force is greater the closer you get to earth. So that's what happens on the center of the earth. But what if we go inside the earth? And inside a planet, the actual gravitational field of the planet decreases to zero. And how can that be? And that's because as you travel from the surface towards the center of the planet, let's say you get here about halfway. Well, now the pull of the mass from the center of the planet here is kind of canceled out by the pull of the mass up here. So the closer you get to the center, the less gravitational pull because it's starting to be canceled out by the mass above you. So let's experiment with this, and let's say that we were able to dig a hole through the planet all the way through, and it's a frictionless hole. Okay, so what would happen if standing at that hole we jumped in? Okay, well, as we fell, our acceleration would start to decrease. Okay, because the force of gravity would start being less. So here on the surface of the planet, the gravity is g. Okay, once we get halfway down, the gravity is divided by 2. And then at the center, if we're at the very center of the planet, the pull of gravity of the entire mass is canceled out by the rest of the mass. So our acceleration is going to be 0. Now remember, our acceleration is going to be 0, but we still have some velocity. We're still moving. And we would have enough velocity to keep us going outside, because as we reached here, as we passed the center, then we would start having gravity start pulling on us again until the force of gravity here was g again. And theoretically, if you had a frictionless hole with no air going all the way through a planet and you jumped in, you would just keep ping-ponging back and forth forever as your acceleration would go to 0, and then it'd decrease again till you got to the other side, and then it would decrease to 0 till you came to the other side and increased again, and back and forth. So you could just ping pong back and forth through the center of this planet forever. And then as we go from the center of the planet to the surface, now again the gravitational field is going to start increasing again. So at the surface is where our gravitational field is at a maximum, the surface of any object, whether it's a planet or the sun. Okay? So, and as we go in, the gravitational field decreases. And also, as we leave the planet or leave the surface, the greater the distance, again, our gravitational field is going to decrease. Inside the planet, our gravitational field is directly proportional to the radial distance from the center. So again, at the surface of the planet, it's 1g. Halfway to the center, it's half a g. At the center, it's 0. Because now, if you're at the center, your radial distance is 0. Okay. And then if you are half the way from the distance, it's 0.5, etc. But now outside the planet, again, we're going to do that inverse square law. So it's going to, the gravitational field is inversely proportional to the square of the distance from the planet. Okay. So here we see in this graph, as we move from the center towards the to the surface of the planet, the gravitational field increases. Okay. And at the surface of the planet, the gravitational field at that radius is the greatest. Then as we move away from the planet. Okay, so now we have 2 radii, a distance of 2. 2 times 2 is 4. So what is the strength of the gravitational field here? It's going to be 1/4. 3 radius away, so we going to square our distance. 3 times 3 is 9. and it's inversely proportional. So now our gravitational field here at 3 radius is going to be 1/9 of what it is at the surface. So it's kind of hard to think what is actually causing this gravitational field? Why are these masses pulling towards each other? And Einstein thought about this field. And so in the Newtonian version of gravity, objects are attracted to each other. So it's a product of their mass that they want to come together. But Einstein looked at it a different way. He said, let's look at gravity this way. Let's say we have a bowling ball and we have a nice soft mattress. And if we put our bowling ball on the mattress, what happens? The bowling ball makes a dent in the surface of the mattress. Okay? And so Einstein said this is what is happening with gravity. When we have a massive object like a bowling ball, it's putting a dent in space time. Okay? And if we have another object like a marble and we roll it across the bed, what's going to happen? Well, it's going to roll into the dent towards the bowling ball, right? And Newton would say that and said the bowling ball is attracting the marble. But Einstein looks at it and says, no, the marble is just rolling in the dent in space time. Okay. So actually, in Einstein's theory, it really doesn't have to do so much with the inherent mass of the object as it does the dent in space time that object made. So if we had something where we could kind of use some CGI to erase part of that picture before, if we could just see the ball and marble interacting with each other. So here's the bowling ball, and we would see the marble coming closer to the ball. Okay. And we would say, oh, the marble is attracted to the ball, which was what Newton's vision of gravity. But now if we use CGI to erase the ball, but we could still see the bed, we would say, oh, the marble is moving in a curve because of the dent in the bed. And that's Einstein's vision of gravity. So let's move on now to another concept in gravity, which is called black holes. And if you took astronomy in college or high school, you might know that all stars have a lifetime. And after they have burned out their helium and hydrogen, they shrink. They start to compress. Okay? As the star shrinks at the end of its lifetime, it still has the same mass. It's just concentrated in a smaller radius because it doesn't have that pressure of the nuclear fission pushing out. Okay. So if we have a person, indestructible person, standing on this star as it's shrinking, we can see, okay, he's exerting a force of 10,000 newtons. Okay. As the radius gets smaller, now all of a sudden it's the same mass, but the radius is smaller. He's exerting a force of 40,000 newtons. The gravitational force is going to increase because our force is equal, remember, to the gravitational constant of two masses multiplied together divided by the distance squared between them. We've kept the masses the same here, but we've decreased the distance. Okay? So because we decreased the distance by 1/2, we square that distance, we've increased the force 4 times. Some stars are massive enough that they become so small and so dense that the gravitational force of the surface is so large that nothing can escape. Anything that gets close enough to that star will be attracted by that warped space-time and, as far as we know, lost or destroyed forever. We don't know where things go. And some of these stars can have gravitational forces so powerful that not even light itself can escape um, the attraction of this star. And that's why we call them black holes, because we can't see them because not even light is coming from them. A black hole can't be more massive than the original star. We can't create more mass here. So if we have regions at the star's original radius and further out, the gravitational pull they feel is exactly the same. but anything that's within the original star's radius is going to be drawn into that hole, even light. And so the star's original radius is called the event horizon. And this is where, to escape the pull of that star, an object would have to have a velocity that exceeds the speed of light, which, as far as we know, nothing does. So nothing can escape once it passes the event horizon.